Well, in the last lecture I discussed you how a eutectic alloy will solidify. So now let us move on to the hypo-eutectic alloy first. I hope it is clear for you how things happens. I am not yet, I have again shown you this picture at a temperature below eutectic transformation temperature. This is what the colonies will form, and you can get this fine microstructure. Okay, so let us now start for the hypo-eutectic alloy. What I mean to say is this one, okay, this one. As you see here, if you cool down this alloy from the liquid state, this is completely liquid state. As you cool down this alloy, nothing should happen below this temperature. This is the liquidus temperature, TL, or the melting temperature of this alloy, in which whole thing will become liquid. Nothing should happen. So this is what is the picture above TL. Everything is liquid. Now if I drop the temperature slightly below the liquidus, slightly, not much. Okay, I write slightly below the liquidus. What will happen? This will be inside this alpha plus liquid phase field. Okay, I have done little bit here, so I have suppose here. So this is just below the liquidus temperature. So but I am within the liquid plus alpha phase field. Okay, so that means alpha will nucleate, because alpha is the only solid. Alpha is the only solid present. So alpha will nucleate and form and grow in the liquid. So alpha nucleates here at different positions, suppose in the liquid, because obviously not one alpha will nucleate, many, and these alpha things will grow like a dendrite. Why they will grow like a dendrite? That is because this is the most common structure which forms in solidified product as a dendrite, a tree-like structure. Okay, they are like a tree. You have seen Christmas tree, so this is like a Christmas tree. They form like a tree-like structure, so they will grow and become. So these are the alpha dendrites growing into the liquid. They will keep on growing till the eutectic temperature is reached. So I was little bit below the eutectic liquidus temperature, and this was the picture. Now this will happen from this temperature to above eutectic temperature. Okay, nothing will happen. But one thing I must tell you, let me just remove these things and tell you, this is my alpha plus liquid phase field. Okay, let me just tell you what will happen. As you go down the temperature, I already discussed you that the liquid composition will change like this, solid composition will change like this. This is the solidus of alpha, this is the liquidus of alpha. Okay, please do not forget that this is the solidus, this is the liquidus, this is also solidus. Now because the temperature is dropping, the solid composition will be given by the solidus, liquid composition will be given by the liquidus. So these are the different tie lines I have drawn. Tie line means lines parallel to the x-axis. So as each tie line, this is solid composition, this is liquid composition, solid composition, liquid composition, solid composition, liquid composition. But overall what we absorb, the liquid composition is keep on increasing in B concentration, XP concentration. Solid composition also keep on increasing in XP concentration. And when the temperature will reach TE, the composition also reach CE. So at TE we will have a solid alpha, and the composition of the liquid at, let me draw it again, for otherwise you will not be able to understand. So this is just above TE, just above TE. You have these dendrites which have grown much bigger. Okay, so just above T we will have, and this liquid whatever present here, this liquid will have concentration same as CE, concentration same as CE, concentration of the liquid is going down this way. So as at the above the temperature, eutectic temperature, concentration will be CE. So now if you cool down below the eutectic temperature little bit, what will happen? This liquid whatever is present here in this liquid, this will transform in the eutectic reaction. okay, they will undergo eutectic reaction, and because of that you will have eutectic microstructure. So, eutectic will form, again I am drawing lamella eutectic here. So, white black, this one also, okay. Let me draw here also. So, what you have is basically alpha dendrites, this is also alpha, dendrites, and in between the alpha dendrites you have eutectic, the liquid which is present here at the undergone eutectic. So, this is what will happen when you cool down the liquid, which is cool down the alloy, which is hyper-eutectic compositions. That is what you see for aluminum silicon alloy. Aluminum silicon hyper-eutectic alloys will have aluminum dendrites, and in between you have eutectics. This is exactly you have seen in the microstructure which I have shown you. So, question is this: if I vary the concentration from this to this, that means little less than eutectic and till this point, this is exactly will happen. Only thing will change is that volume fraction or the amount of this alpha phase and the eutectic will change. Okay, let me also tell you this alpha, which forms as a dendritic way above the eutectic temperature, is known as a primary alpha, remember that, or pro-eutectic alpha. Pro means before. So, this alpha which forms above the eutectic temperature as a dendritic manner in the liquid is known as a primary or pro-eutectic alpha. Please do not forget that. And in the eutectic also you have alpha and beta. Okay, suppose this is alpha and this is beta, the black one, the white one is beta, the green one is alpha, the way I have drawn. So, this is called eutectic alpha, this is called pro-eutectic alpha or dendritic alpha. You have to be very clearly, you have to think about eutectic alpha and pro-eutectic alpha or primary alpha. So, primary one will come as a dendrite and eutectic one will come as a lamellar or rod, whatever when the morphology of eutectic, but normally as a lamellar eutectic. Aluminum silicon, it will come as a acicular eutectic. So, in the whole microstructure is connected to the phase diagram, that is the beauty of that. So, if you understand the phase diagram nicely, you can generate the microstructure and control it, and if you can control the microstructure, that means you can prepare, you can get any properties you want, correct. So, I hope it is clear to you that how these things will happen. Remember that here also you can have coring, I told you coring in alpha, okay. Here also it is possible to have coring in alpha. What is the meaning of coring? Alpha dendrite which will form, I go back to the discussion on copper nickel isomorphous system and look at the video lecture which I have given earlier. There you will see that these alpha dendrites are cored, okay. Core means the compositional gradient exists in the alpha dendrites. Same thing can happen here also, and because of coring, suppose this is the concentration of the alloy, we can change the phase diagram, and phase diagram will be looking like this, okay, like this. I have drawn a solid line, and in that sense the solidification will get over even lower than the eutectic temperature, because this is the temperature here. So, this will be coming down, okay, like this way, and this will modify the whole reaction. So, let us not discuss and complicate the stuff right now, but I am telling you that the possibility of real life situation, this will be the actual thing happening. That means you have a extended solidus line like this because of coring effect, and the solidification temperature will go down the eutectic temperature. This is possible, but this is an advanced topic which I will not discuss much. It is not there in the books also, but this is possible. Now, let us go back or go to the, sorry, not back, go to the hyper-eutectic concentrations, and I remove this these things now, these pictures little bit, but I will not remove the whole thing, I will explain it how things happens. So again here alloy composition is suppose this one I have discussed, this dotted line is the hypo-eutectic. You see nothing will happen above the liquidus temperature. Here the liquidus temperature is this T dust L I have written because this is TL I have marked. T dust L is the liquidus temperature here for this alloy, and nothing will happen above this temperature, everything will remain as a liquid. Okay. So above T dust L everything will remain as a liquid. Now as you go down the T dust L slightly, you will have beta dendrites forming instead of alpha. So these dendrites will be beta. Okay. These are all beta instead of alpha. Beta dendrites will form. Am I clear? Because it is liquid is in equilibrium with beta. Liquid is equilibrium beta. Please remember this. Liquid is in equilibrium with beta. Therefore, if you cool down below the liquidus temperature, beta will nucleate and grow, and it will grow like a dendritic manner again in a solid, in a solidification situation. And same, these dendrites will keep on growing from this TL star, TL1, TL dash to TE, this temperature range. Okay, from this to this temperature range, from here to there, it will grow, and they will become bigger. These are all beta. Slightly above the eutectic temperature, this is what is the microstructure. Now as you see here, as I can draw here again the tie lines like this. Okay, let me just remove this liquid plus beta, the phase field. So this is liquid plus beta. So I can draw these tie lines like this, and as you see here, as the beta grows, the liquid concentration will change along this line, along this curve, because this is the liquidus of beta. Okay, and this is the solidus of beta. So because of liquidus of beta is like this, the liquid concentration will keep on decrease in B concentration, because B is reducing this side. So because of that it will reduce. On the other hand, beta, solid beta, B concentration also will decrease. This is a little bit confusing, but this is what exactly happens in the actual stuff. So liquid will be lean in B, and finally at TE temperature liquid will have concentration of CE, because this is going down. So that will happen, this liquid will have concentration of CE concentration. So just below the eutectic temperature again same thing will happen, the liquid which is present will become eutectic, correct. So these are all beta dendrites, and the eutectic which is there in between will become like a eutectic, lamellar eutectic between alpha and beta. So similar way what I have discussed for alpha, these beta dendrites are called pro-eutectic beta or primary beta. On the other hand, beta which is like this white lines, they are known as eutectic beta. So you have clearly understood that from hypo to hyper, only difference is that the dendrites are changing. In the hypo concentration, dendrites are alpha, in hyper concentration dendrites are beta. That is the only difference. Microstructure remains same. So in aluminum silicon, this is what exactly I showed you. For hypo aluminum silicon alloys, you have aluminum dendrites and aluminum silicon eutectic presence. On the hyper one, you have silicon doesn't go as a dendrite, but it goes like a faceted phase, silicon and dendritic phase of aluminum silicon. This is what exactly happens. So by this picture, by this way, I can explain all my alloys which will solidify. Only one thing I have not discussed, which I will do it right now, which is little bit complex, but before that I remove this part, little not complex, little bit different from these two. So I remove all these things now, and I remove that. So I have discussed with you eutectic, hypo-eutectic, hyper-eutectic alloys, but there are one set of alloy here which is like this, okay, which does not go eutectic reaction. Here also is present, it does not go any eutectic reaction. So any alloy concentration, any alloy composition which has concentration less than this one, this point, or this point will not undergo this reaction, please remember that. And these two lines you see here, this is one curve or line, whatever way, curve is better way, they are known as solvus, SOLVUS. This is solvus of alpha, this is solvus of beta. Why it is called solvus? Because this tells you the concentration of solid alpha as a function of temperature. So you can see here at eutectic temperature it contains largest amount of solute B, at room temperature it contains least amount of solute B. Same thing is valid for beta. At room temperature it contains largest amount of solute A, at room temperature it contains least amount of solute A. So it is very clear that these two alloys or these set of alloys will not undergo any eutectic reaction. They will solidify just like isomorphous alloys, I discussed with you, exactly that way. So in a nutshell I can say there are actually 5 different alloys, 1, 2, hyper-eutectic, eutectic. So if you want to discuss the whole thing, you have to discuss 5 different alloys, which I have done in my whole discussions. So now the only thing I will now discuss is go back to my slides, and with your knowledge which I have discussed now, I will again go back and discuss, show you this microstructure and tell you how they are formed. Okay, so let us now start with this picture. As you see here, this is a eutectic alloy which has a lamellar microstructure of different grains here, you can see here different grains of lamellar type, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 grains are there. Okay. But on the other hand, hypo-eutectic alloy, if you see, suppose this alloy 2, which is the hypo-eutectic alloy, if you cool it down from a liquid at point A, it is a complete 100% liquid, and just below the liquidus temperature, this is the liquidus temperature, you have a pro-eutectic alpha present, even the values of volume fraction values are given, amount fractions are given, which we will do in the next class calculations, or rather we will apply lever rule to calculate that. So you can see here from point B to point D, what has happened, the pro-eutectic alpha phase has grown like a dendritic manner and rest of the liquid has remained. So at just above the eutectic temperature TE or at point D, the liquid will have concentration given by this point CE, or here lead tin is basically 61%, 1.9% tin. So once you cool down below the eutectic temperature, this will solidify like eutectic, the liquid which remain, and along with these dendrites of alpha will be present. That is what is called pro-eutectic alpha or primary alpha, and the other one as eutectic alpha. Same thing will happen on this side for a hyper-eutectic. So in a hyper-eutectic situation, except alpha, beta will present, other than alpha, beta will present, but eutectic will remain the same. Okay, now let me just go back. So this is the lamellar eutectic. If you take a completely eutectic composition, you will form a lamella 1. Okay, now you can also form a rod. So let me just go back to the aluminum silicon. Yes, this is aluminum silicon phase diagrams, very interesting and very widely used. You see here, this is a hypo, this is a hyper-eutectic alloy, silicon is a pure on the right side. So hypo 1, let us see, hypo 1 will have aluminum dendrites and the aluminum silicon eutectic, exactly the way I shown you. So these dendrites have formed and grown above the eutectic temperature, that is why they are primary aluminum dendrites, and this eutectic which is there in between you have eutectic which is acicular type or fibrous type, silicon grows like a needle here. So this is what the eutectic. Same thing here shown here, you have a long aluminum dendrites and you have fibers. Okay, now if I take a hyper-eutectic, I told you hyper means there will be no alpha aluminum or aluminum, it will be silicon as a dendrite. That is what you see here, silicon as a dendrite, and silicon does not go like aluminum dendrites because silicon is a metalloid, it goes like a faceted dendrite. You can see here sharp faces, very sharp faces, some they have triangular, some have rectangular, some have even this kind of trapezoidal shaped, all kinds of face shapes are possible, and in between that you have a eutectic between silicon and aluminum. So here this silicon which is present as a faceted big grey things is called primary or pro-eutectic silicon, and the silicon which is present in the dendrites are eutectic, sorry not eutectic, are called eutectic silicon. So there are two different types of silicon, one is eutectic silicon, other is a primary silicon. Similarly here also you have a primary aluminum, eutectic aluminum. Okay. So it is very clear that this is the way the microstructure will form in the eutectic phase diagrams. So with this I just want to say that this is a very important lesson, and you must must try to understand what have I told you. I have discussed very lucid manner. Please try to understand, because eutectic is a very important alloy system in material science, and if you understand this alloy system very well, because most of our alloys which used in real life like cast iron, aluminum, silicon and lead tin, they are actually eutectic alloy systems. So if you know the phase diagram and understand the microstructure formation very well, then we can actually control them. That is the basic idea of such a kind of course, and which you should be able to understand. With this, next class I am going to discuss with you little discussion of aluminum silicon eutectic and their modification, and finally I will also draw the free energy composition diagrams so that you can understand it. Okay.